For every question, please pause the video to read the question and try to solve it on your own. After that, replay it to show yourself the solution. Threshold frequency is minimum frequency to emit electrons from metal surface. To calculate this threshold frequency, and all we have here is frequency of incident light and stopping potential of electrons, we will use the equation HF, which is energy of photon, equal to HF node, which is the work function, plus kinetic energy of emitted electrons, which is the same of stopping potential multiplied by electron charge. We can rearrange and find F node. For total number of bright spots, we need to find all spots on right from 0 to 90 degree diffraction angle, and the same on left. We can, for the symmetry, find what is on right and multiply by 2, plus adding the zeros spot. So here is a lambda equal d sine theta. D will be 1 over 280, and this 280 divided by 10 to minus 3 to convert the millimeter to meter, so it goes up to the numerator here. This is the spacing D after conversion, and lambda here in meter, so only left is theta to be 90, so sine theta is 1. Okay. On both sides, it will be the answer here times 2, and adding 1 as we said for the central spot. Y lambda in D greater than in S, because we have same source, so same frequency, and we have speed in S less than D, as mentioned here. We've traveled more slowly in shallow than in deep. And we have V equal lambda F, or lambda equal V over F. F is the same, so lambda directly proportional to V. So lambda follows same relation as V. You should correct theta S here to theta D and D to S. This is a typo error. And to find theta D and theta S, if we looked to the graph here, we have for the incidence the angle between the interface and the wavefront. Here is the interface, here is the wavefront, is 53. And if we draw a perpendicular and draw a direction of incidence, we will find that this angle here between the wavefront and perpendicular is 90 degree minus 53, because perpendicular has a 90 degree angle with the interface, and if this 53, so this will be 37. Okay, this angle is 37. Now look to the 90 degree between the interface and incidence direction. Okay, it is 90 degree minus 37, so it is 53. So incidence angle is like angle between interface and wave front, both are 53. For the refraction direction here, we have a 90-degree angle with the wave front, and again we have a 90-degree angle between the direction of refraction here or here, any direction that is parallel as perpendicular has a 90-degree angle with the wave front. But here for refraction we only care about the geometry here, perpendicular with wave front, okay, is 59. So for this perpendicular, which is certainly parallel to this, and this wave front, which is also parallel to this, we have the shaded red angle as 59. And we have, as I said, 90 between refraction direction and wave front. So this angle, which is the angle of refraction, is 90 minus 51, 59. It will be 31. So theta d, angle of incidence, is 53. 31 is angle of refraction. We can substitute here and we'll find the answer 1.55, which is also the refractive index. Determine the period of oscillation and explain. So many students firstly think that it is just the time between peak and 1.25, but you should note that simple pendulum, when we draw a graph that looks sinusoidal like the graph here, it is in simple pendulum between the horizontal displacement, okay, and the time. But here in this question, it is between the vertical displacement, okay, and the time. So you may notice that we have here the curve in both positive and negative direction. Here is 0, okay, but in this case we don't have negative value. We have all values positive. So we can start from left at T0 here, reach to the equilibrium, which is the minimum value of H, okay, and then increase in H again, and then return back to the minimum value, the equilibrium. Minimum value of H is the equilibrium, and then goes to left again, okay. So it is not a 4-segment oscillation for segment on graph, it is 8-segment oscillation. Far left to equilibrium, equilibrium to far right to equilibrium, equilibrium to far left. 1, 2, 3, 4. If we looked for each of them, total length, if we looked as halves like here, it will be 8. Anyway, don't bother. to find the period, you should go from some point and return back to the same point. So from here, not to this point, this is the far right, to this point is the right answer, which is 2.5. Assume time period for the swing is same as for simple pendulum for length L, and find L, which is the length of the chain here in this question. We have the formula for simple pendulum. To find L, we simply rearrange, okay, and it is easy to find the answer. Why swing doesn't behave like simple pendulum exactly? Because we have oscillation is dampened. You notice that amplitude is shortened with time, and also it is driven. Certainly the child pushes the ground. Angle is not small. Child not a point mass. He or she left shifts is center of mass. Okay, all of these reasons are contributing to make a difference between simple pendulum and the swing. Chain also is not massless and not taut all the time. Maybe somehow relaxed or bended. To draw kinetic energy, okay, versus time for this oscillation, let me draw once again the shape of oscillation. It was like this. H versus time. We know always that at equilibrium we have the highest velocity, so maximum kinetic energy, and at the far right or far left, or in this example, this question, in the highest values of H, amplitudes, I mean, velocity is zero and kinetic energy is zero. So if we begin by maximum H, we begin kinetic energy by zero. Here we reach the equilibrium. This was at almost 0.6. Okay, so we reach here the maximum value of kinetic energy at 1.6. After that, we reach the far right, return back to equilibrium at 1.2. Okay, I suppose no. Here is the 1.2 because segments are equal, so this is the 1.2, this is the 1.8 almost, and this is the 2.5. Okay, we have for the kinetic energy started with 0 at maximum, and the maximum at 0, and then 0 again at maximum, and then maximum at 0, and finally, okay, here we have 0 at 2.5. Okay. In polarization, oscillation is restricted to certain plane that is perpendicular to wave propagation. In longitudinal, oscillation is parallel to wave propagation, so we cannot make it restricted to a plane perpendicular to propagation. Antenna must be aligned with polarized signal for signal transmission, and mobile can be held in different orientation. So microwave transmitted to mobile phone must not be polarized in a single plane. Okay, we have the relation VB minus IR equal to V. Okay, so if we try to draw a relation between I as the X and V as Y, we have an intercept from Y here, which is VB. This is the 1.6 volt, and we have the slope here to be minus R. The slope here is negative, and minus R is negative, so the value will be positive. So EMF is 1.6, and the slope, as I said, is R small. Okay, as we have RV less than RA, so we have the R total B to be less than R total A. Okay, let me just draw a cell, whether it is A or B, with an external resistance. Okay, and you can imagine another circuit for B. Okay. R total B less than R total A, so current in circuit B will be greater than A, and lamp B brightness will be greater than A. As we see the red spot here, this means that there is a total internal reflection. And to draw this, we just incident the light here, make a perpendicular, make an angle of incidence equal to angle of reflection, and repeat same process every time the ray meets the wall of the water jet. So as the red spot appear on screen, we can deduce that there is a refraction. Okay, total internal reflection field here, and it is a refraction, simple refraction. So incident light on the interface here, and we can draw a perpendicular to make the refracted ray away from this perpendicular, make this angle greater than this angle as much as you could. Why total internal reflection failed here? Because certainly incidence angle is less than critical angle, and why it continues to be away from normal, because we have velocity of light certainly in water jet would be less than that in air. So as velocity in air greater, light refracts away from normal. Don't ever point laser to audience. You can add also that don't use reflective surfaces. Progressive and stationary. Progressive transfer energy, stationary not. Progressive has beacon troughs or compression and rarefaction that moves, but standing waves not. It only has nodes and anti-nodes. We can say also that all points can have same amplitude sometime, but a amplitude varies along the wave. All points cannot have this amplitude with time. They differ. Points in medium where standing waveform differ in amplitude along with the time, and they cannot for some point to be varies in amplitude of displacement and reach same amplitude. Phase varies, but it is constant between adjacent nodes or antinodes. Don't forget to include these requirements, measurements, okay, instruments, how to reduce uncertainty, and commenting on the graphical method. Okay, we will first vary mass by adding known masses to vary tension, where tension is given by mg, and we will vary the frequency from function generator or signal generator slowly to spot a zero harmonic. We will repeat these two steps for 6 different masses and measure L by rule. And when we do this, we should look perpendicular to avoid parallax. After that, we have the relation f equal 1 over 2L square root of T over mu. We can rearrange it to plot a relation between frequency on y-axis and square root of t on x-axis. So we will have the slope 1 over 2 square root of mu. And to get the mu, we can rearrange by this way. While using second harmonic, will reduce random error because second harmonic has node in its center and it is easier to observe a node than anti-node.